Greetings, welcome to Inference for Categorical Data Part 3. So in this part of our little exercise or our little laboratory foray here, we're going to go ahead and take a look at problem 610. Again, another problem that has been in the news, what's going on in Greece. So 6.10. Life rating in Greece. Greece has faced a severe economic crisis since the end of 2009. A Gallup poll surveyed 1,000 randomly sampled Greeks in 2011 and found that 25% of them said that they would rate their lives poorly enough to be considered suffering. In other words, 25% of the population rated that said basically we are suffering. Okay, so they want us first of all to describe the parameter of interest and what is the value of the point estimate of the parameter. Okay, so the parameter of interest. So the parameter of interest is the population proportion of Greeks who are suffering. So we'll put quotes on the suffering here. So we're taking that straight from the thing. Okay, so they ask us what is the value of this parameter. So we're going to need it, the point estimate of the parameter. Excuse me. We're going to need this in the future steps here. So let's go ahead and get a chunk right now, and we'll go ahead and just do it right here. And we're going to say we're going to call that p hat. And well, what is p hat? Well, p hat is going to be the proportion, the sample proportion of successes. Okay, so it's 25% in this case, or 0.25. So p hat is equal to 0.25. So that's all we're going to do is just make ourselves a new variable, and we're going to call it p hat. Nothing fancy. All right. All right, cool. So they want us to go through and they want us to check the conditions for constructing a confidence interval based upon these data and see whether they are met or not. All right, so what are our criteria? Well, we need to have independence in a simple random sample. We can roll with that. Gallup did this. They do this for a living. They wouldn't be doing this if they didn't know what they were doing. So we can go, okay, Gallup, if you just want to, did the poll. So the independence is pretty good. So it's got to be good. Like I said, they don't do it. You know, they're not amateurs. They know what they're doing. Okay, but let's go ahead and check the success failure criteria. So the success failure criteria, how do they fare with that? In other words, what does that look like? So we'll go ahead and do that using an R chunk, just to kind of drive home what that actually is. Well, remember to do the success failure criteria. What we need to do is take n, which in this case was 1,000. So we had 1,000 people, just to go back up and remind you, it was a sample of 1,000. And the p here was equal to 0.25. So there's our n times p. And then we also need to check the number of trials, so sample size. Again, remember that you be sure you keep this straight, that we're working with a binomial distribution again here, that each of those individual Greeks were a Bernoulli trial. They either answered, one or the other. They were suffering or they were not. That's the way we're approaching this. Okay, so success is to find somebody who was suffering, which is counterintuitive, but that's the way stats works, right? Okay, and so that's equal to 75%. That's your 1 minus p. I mean, maybe just to drive it home for you, it's what? 1 minus 0.25, which we know is 0.75. I could do it in my head, but that's where the 0.75 came from. So if we run that chunk, we get back 25 and 75, excuse me, 250 and 750 respectively. And so, yes, the success failure criteria is met. Type really I can. All right, so all of those are met, and so now they want us to come down here and they want us to come in and actually construct the confidence interval. Okay, so we'll go ahead and do that using an R chunk. So we'll insert a chunk. Now we defined p hat earlier, so that's going to make our lives a little bit easier because we're going to need to use that value of p hat many places in the calculation. So we'll go ahead and just do that and kind of make it so that it's ubiquitous to it. Okay, so I'm going to find a new variable. I'm going to call it u for upper, for the upper limit of the confidence interval, and that's going to be equal to our point estimate, where our point estimate is what? That's p hat. You can put in the 0.25 there if you feel more comfortable with it, but I think it just kind of drives home actually how we're doing this, times the z star. Remember how we do this. The confidence interval is constructed by taking the point estimate plus or minus the margin of error. And our margin of error for a 95% confidence interval working with z, we know that the z star is going to be what? 1.96, right? Times our estimate of the standard error, and that's going to be SQRT for square root of the p hat times 1 minus p hat divided by the sample size. We know that the sample size in this case was 1,000. Now you could just very well as easily put in 0.25 and 0.75 for the p hat and the 1 minus p hat here, but I wanted you to see the structure behind it. I think that's going to be useful as we move through this chapter. Okay, all right, and then let's go ahead, and I'm just cutting and pasting it, and I'm going to make the lower limit down here, and notice that the only difference between the lower limit and the upper limit was that I have a subtraction instead of an addition. And then I will display, have it kick it back out to the screen by doing L comma C. Be sure and keep it as capitals and lower cases. Okay, so if we go ahead and run that chunk, let's see if I did everything correctly here. Something's not happy. It doesn't like what I did. What did I do wrong there? Okay, duh. I put a C there. What was I thinking? I needed a U there. Okay, I just paused it for a minute and looked at it to see what the hell did I do wrong. Okay, let's try that again. There we go. So there's a confidence interval. So our confidence interval says that between 22.3% and 27.7% of Greeks would classify themselves as suffering. Okay. All right, so that would be the confidence interval. We don't really need to do any more. They didn't ask us for any more interpretation, just what those numbers were, so we'll roll with that. So without doing any calculations, describe what would happen to the confidence interval if we decide to use a higher confidence level. So remember our analogy back when we first started talking about this, that confidence intervals are like fishing with a net, and if you have a higher level of confidence and you're catching fish, that must mean you had a bigger or wider net. Okay, so by increasing your confidence level, you would increase the width of the confidence interval. Okay, so you would increase the width of the CI. Okay, you would make it wider. Okay, so again, without doing any calculations, describe what would happen to the confidence interval if you used a larger sample. This one's a little less intuitive. We haven't talked about it quite as much, but you got to think about how the standard error is being calculated. It's p hat times 1 minus p hat divided by n. So the denominator is n, and so if you increase the denominator, it makes the number smaller. And so by increasing your sample size, you make your standard error smaller, thereby making your margin of error smaller. So this would decrease the width, and that's going to make it narrower. And if you think about it, that kind of intuitively does make a lot of sense, because the more larger your sample is, the more precision you would expect out of your confidence interval. More precision meaning that you would have a narrower interval, or less slop, so to speak. Okay, so that's our first foray into calculating a confidence interval for the population proportion with a single proportion. Excellent stuff to put into your reference book, and I will be back here soon with another one for you.